Yes, it's working. It's okay. Okay, you will start. Thank you for the chance today to being here in the conference. I will try to be fast as possible as I can. I am here today to share a part of our research with numerical co-simulation using FMI standard to enhance the efficiency in marine hybrid propulsion and onboard electric network. So my name is Amer Haidar. I am the marine and KE engineer, and my partner and co-author is Professor Michel Lindman, but is not with us today, so I'll present the total of work. Okay, so our presentation, this presentation is a part of Upland project. This project is now being in progress in University of Applied Science Berlin with partnership with BSS company and is supported from the Federal Ministry of Economic Affairs and Energy in Germany. So our main goal in Upland project, it was to create and develop the simulation-based tool which can help the designer to optimize the electric and hybrid watercraft, and of course to optimize the connections on board power supply systems. So for our agenda, I will just try to pass these points very quickly also. So for our introduction, so hybrid propulsion now, it's a key factor, it's a key enabler for our CO2 reductions and emission reductions, and of course our decarbonizations. And from that, we are trying an Upland to simulate the full electric, the serial hybrid, and the parallel hybrid boats in one model-based tool. This tool can also respect all the requirements, the basic requirements you can see here. So the model should predict the current profiles and temperature profiles for all the high power consumers. Our model should support the co-simulation. It should be adapted in open and closed loop simulation, and of course allow the users and the designers to control all the vessel operating conditions, and should be validated and verified using various types of hybrid boats. So there is no standard configuration for the hybrid propulsion system. And after a long phase of research and analyzing in the industry markets, so we could at least we could arrive to this maybe this general system propulsion. This system which contains the internal combustion engine, which contain the motor generator, electric motor, and will contain also the shaft generator, will contain the battery pack, the low voltage system, the high voltage system, and of course converters, inverters, and we have also the mechanical power distribution and electrical power distribution unit. So we can control the different types of power during the navigation of the boat. Of course, every equipment here, so you can connect and disconnect it in the model. It depends on your model. So if you have a full electric boat, you can just disconnect the ICE and its gearbox and clutch, and so now the boat will navigate using the battery energy. And of course, if you have the full classical boat with diesel, so you have to connect this. You can easily disconnect the battery and just navigate with the ICE. Of course, this model can support the full electric drive, full ICE drive, the posting mode, so using both drive and service, the battery charging with ICE drive, and recuperation mode. And this mode, it was just to test the flexibility of our model. So of course, for sailing boat, so does the propeller can take also the energy from the water and transfer it, of course, by converters to charge the battery. Okay. It's working. For hydrodynamic controls, of course, to make the model as simple as we can, so the vessel motion have been presented using the 3 degrees of freedoms, so in surge, sway, and yaw rotation about X. The boat dimensions, specifications, as well as, of course, the propeller, the rudder, and all other equipments and coefficients, so they will be controlled so directly and easily in one initialization file, which is combined with our model. For navigation control, of course, we have a different control cycle to drive our boats, but we can propose the major the control cycle here. We have the longitudinal speed cycle. This longitudinal speed cycle, it's very useful to test our model. So we can test the maximum power of the engine, the maximum capacity of the battery, and of course, we can test our propeller, and every part is working alone, is working well. But for the real operation of small size boats, so we have another cycle, which is the velocity and rudder angle cycle. So for small size boats, the driver, the captain, so that can easily change the velocity cycle with time or the rudder angle with time. So he can do that to test, to control the boat. But for medium and large size marine vessels, of course, it's not like in this shape. So we have the control cycle point tracking. So the user can define a point tracking course for the boat and just watch the boat so crossing this way from point to point till the destination one. And of course, there is a water current speed to control the water current in the environment, and of course to test the recuperation energy mode. For verification and validation, of course, verification and validation still till now in progress. Of course, we have to start in our model from power and energy conservations. So under different operating cycle and scenarios, so always our power error or the difference between the input power and the output power in the model should be almost zero or very, very, very small. And of course, we have another step of validation, so the point tracking. So we have defined also a various of point track courses and cycles, and we were checking also our boat. So does our boat really following the tracking point as much as close he can? And so and you can see here, so between the requested routes and the actual route of the boat. And of course, another step of validation, it was to use the complete operational data for one boat. So we have the operational data for the engine of Nord Traveler ship. This data we have entered in the boat in our model, and we have checked if our operational condition exactly matching the operational operational diagram and load diagram coming from of course, from the manufacturer or from the engine. For model co-simulation, of course, it was a key objective for our Optland project to make our model also adaptable for functional mock-up unit. So that's why we have here two directions of co-simulation. So we can start from our hybrid vessel model in MATLAB simulating platform, data exchange to FMU model, and with this model will be also exchanged to be tested or run it in other platforms like FMBY tool or like Skilab, Daimola, or even CFD analysis like OpenFOAM or ANSYS Fluent or others. The second direction, it was to, of course, which out of our focus for this presentation, which is using some CFD analysis to simulate the propeller behavior and delivery power of this propeller and give it again to the MATLAB simulating model. So for our focus in the first direction, so we can validate and run our model in Simulink platform, and of course in another platforms like Skilab, open source one, or Daimola, and of course for FMBY Python open source platform. For open loop co-simulation model, after completing the model, and now there is an open loop structure is being developed at the moment. This open loop structure is very helpful for the designer to drive the controller and drive all, so he can connect our FMO boat model with the drive controller FMO file. This allows the user, of course, to control the boat lever, the gearbox of the boat, the steering gear, and the water current. So these files will be inserted and connected to our boat FMO model, and of course you can see now the output signals. So the output signals will be transferred to another FMO, which is our partner PSS tool. This PSS tool will treat and of course translate this data. We have for the output signal, so we have choose of course the electrical current profiles and temperature profiles for all electric cables on the boat. We have also the operational parameter of the vessel, battery status, state of charge and parameters, and of course hybrid propulsion modes, so which mode can the boat navigate. And of course, this open simulation model has been created by Daimler platform. And after that, we are developing the real-time simulator. This real-time simulator presents the co-simulation with Python programming language. This real-time simulator also can be very effective to support the decision making and the design phase. So the user can run the real-time simulator without any modifying or running the original model. And of course, at real time, he can watch all the operational conditions, of course, the current profiles and the temperature profiles, and he can control them. So in case of overheating or overloading an onboard, all the electrical network can be modified, redesigned, and the simulator rerun again. Like a practical case study, so now we finished our first practical case study by inserting the first hybrid boat, which using the parallel hybrid propulsion with dimension, 35 meter length overall and 312-ton displacement. So this boat with his dimension and specification were integrated in our model using 8 cables and the battery pack 315 volt, and of course the e-motor, shaft generator, and the consumers, low volt consumers and high voltage consumers. And as you see here, so we delivered our FMU file to our partner PSS tool, which they have own FMO tool developed also. This tool, it's using the cross-section of the cables, the material, the isolation, and the weigh as a factor. And of course, another more factors for electric cable, like temperature class, cable aging, the environment of around the boat, and the voltage drop and worst case scenario. So like here, we have the design cross-section and we have the optimized cross-section for every cable. And we could optimize almost every cable to use a minimum or a smaller cross-section and cost the saving. So in euro, just in one boat, maybe I can say it's a small boat. It's not even medium-sized boat. And of course, when you have a larger boat, that means more cables, longer cables, and that means more cost saving, of course, with respecting to the standards, safety, and classification. For our future work, so now we have 2 steps in progress. So we are in the phase of implementation, full electric boat in our model, also to test the electrical network on board, and the diesel electric boat, like a serial hybrid system boat. So we will use the both of them to optimize the electrical network and, of course, to do it. And after that, so we'll start our second co-simulation stage to link the CFD analysis with the hybrid boat model. And after that, we will create the full documentation. Of course, we are really interested to engage with all the shipbuilders, designers, and to identify the collaboration opportunities. And so some references, thank you. And yeah, thank you for any more information, interest. We are happy to answer you on this email. Thank you.
Thank you, Amer. Questions, comments? Wishes, criticism?
Oh, that's good. No question, no criticism.
We have one here.
Siegfried has a question or a comment or criticism.
Just a question, will this model be open source? Or?
Yes. Now we are preparing the FMO model to be an open source, and after the validation phase, so we have to finish the validation and verification phase, so we can publish it, of course, and we can contact the more shipbuilders, universities to test it. We will,
Perfect.
We will be happy to have a feedback.
Interesting, yeah.
Thank you.
So my question is about like, how do you want to connect CFD simulations as FMU back to your original system?
Actually, the idea here is to simulate the propeller and the radar interaction using the CFD analysis. It's almost with 3D environment. It's more realistic and more maybe appropriate to the reality. And we want to take the thrust power from the propeller and to take it back. So the real thrust power, it's really difficult to calculate it in real life. So in simulation, it's in MATLAB, it's really difficult to calculate this power and to take in consideration the cavitation, the noise, the sleep of the propeller, and other factors. So in CFD, it's more realistic, it's more powerful. So we are trying to take the energy to the power shaft from the propeller and translate it to the electrical and mechanical system, and that's how we can maybe estimate the real power inside the model. So it will be. Yeah, it's exactly. It's surrogate model. It's also an idea. But maybe I think the CFD can give us at least maybe for a short time, like 1 minute navigational operation, a real operation for the propeller. So it can give us a profile for the propeller, a more accurate profile, and we can extrapolate this propeller this profile from 1 minute, maybe from 1 hour or 2 hours or more. So we can transfer this profile more to inside the model. Exactly.
So I guess that is a surrogate model in a sense then? Yeah.
Yeah, it will be almost in the same way.
Yeah. Cool. Moving on. Thank you very much once again.
Thank you very much. Thank you.